Sometimes in chemistry there are really weird things that happen, and they don't easily make sense. And sometimes we even try and construct explanations that make them simpler when we really shouldn't. So right here I have a 10,000 volt light voltage source that I'm going to put across a light bulb containing a little bit of hydrogen gas. And when I turn this on, you're going to see a light come off of it. And to you it might look pinkish or white or kind of some purplish color. But if you were to look through one of these, a spectroscope, and you were to point it right at the right spot, you would see 4 different colors. You would see 2 purple lines, a teal line, and a red line. And that is a really, really weird thing happening there. So what we want to do today is go through what actually is happening and what can we learn from that really weird experimental data. Now, if you've never seen one of these before, this is a spectrum chart. We're going to go ahead and light it up so you can see it a little better. And this shows what happens when you put 10,000 volts across any different element that's on this list. So the hydrogen one is here. There's a red line, a blue-green line, and then 2 purple. I don't know why this one's a little bit more blue than blue-green, a little orange than red. But when I look through here, it's very clear that that's what those colors are. And so why do we see those 4 colors, and why do we not see other colors? Let's start with kind of constructing a picture here. So we have a hydrogen spectra. Let's go ahead and give ourselves a background here. So we have a red line occurring. We have kind of a teal, and then 2 purple. I don't have purple, so that's going to have to do. Now, sometimes it's hard to resolve those 2, depending on how well you can see in your spectroscope, but those are the 4 visible colors that come off of hydrogen gas. And the fact that it's those 4 and not other things is really, really strange. Let's construct a really simple model here for a second, just to try and show you how strange that would be. Let's assume that the color that we see is based on the particle speed. It's not, but let's try and get across the idea. So when we see red, let's assume that's a hydrogen particle, and the teal is a different hydrogen particle, and we have 2 different purple. Color was in more. So what might be something that causes those to be different? Well, one simple explanation could be that maybe the hydrogen particles, when they're moving slow, give off red light, and then when they're moving a little bit faster, give off this tealish color, and when they're moving really fast, they give off violet light. What that would mean is that you would never be able to have a particle speed in between those 4 speeds. There is no orange, there is no yellow, there is no green. You could only have this speed, this speed, this speed, or this speed. Keeping in mind, of course, that these particles are constantly colliding. So even though this is not actually what's going on, it creates this really weird idea called quantization. And quantization is something that is very confusing and doesn't have a simple analog into our world. And so sometimes people try and create that simple analog to make it more approachable to high school students or middle school students. But maybe we shouldn't. Maybe we should just go, you know what, that's really weird that we only see those 4 different colors. So let's try and construct some complicated explanations that make that work a little better. Okay, so we're going to look at what's happening that's giving off those colors of light, and we're going to look at why you can only have red or teal but not orange, or another color red, or yellow or green or blue. Why only those 4 specific frequencies of visible light are the ones that come away from hydrogen. So if we go to explain this hydrogen a little better, one of the things that's important to keep in mind is you can't actually see an electron. The way that visible light interacts with the electron precludes people from being able to watch and track it. It's not like you can just watch it moving around. And a good analogy that I heard once was, imagine there's a world that's different from ours, a different universe, and in that other universe, that grapefruit are invisible. You can't see them. You're trying to figure out what a grapefruit is. But the one thing you can do is if you take a grapefruit and you smash it with a hammer as hard as you possibly can, and it splatters into little tiny pieces. You can see the little tiny pieces. That's very similar to how an electron works. You can't see an electron, but if you smash it with a hammer, which totally changes what it's doing, then all of a sudden you can see a little tiny piece of it. And some people try and reconstruct those pieces into a visual image of what the electron is, and it's really not going to be helpful or fruitful. All right, so what we want to do is we want to come up with an explanation on how we can quantize electrons, meaning that we can have an electron in a 1 state or a 2 state or a 3 state, but not in between the 2. So for that, I've called in my best friend ever, And my best friend, who's totally real, has agreed to help me show you an example of kind of what that looks like. So I'm going to go, hello, best friend that's real and a person. Okay, so they're going to hold on to this slinky here. And what we're going to do is we're trying, between the two of us, that are both actual people, we're going to come up with a system to describe electrons that gives us this quantization. So when I move the slinky, if I move my hand at a certain frequency, then that slinky is going to resonate. So in this model, the slinky is going to be our electron. Okay, now keep in mind that because this is a wave, it complicates things. Like if I say, where is the electron? Well, it's all over this place. But it's not exactly the same here as it is over here where my hand is. And so it's a little more complicated than that. But we're going to say that for an electron, this is our lowest energy state. And then, if I shake my hand at the right frequency, I will get a second state. We're going to call this an excited state. Now in this one, we have one spot that I want to kind of point out here, and that's right here, where the electron really isn't, or the slinky, is not really doing anything. So here, it's moving up and down, there's a lot of looping going on, or whatever you want to call that. But then there's some other spots where it's not really doing this. So here we have our second energy state. And then if I were to move my hand at a different frequency, we could end up with another one. If I were going even faster, we could probably end up with more. Now if I just were to move my hand, I can do some things that, so if I just kind of send a pulse down and I start to do that and I don't really follow a given pattern, I don't really get anything here. So what I'm trying to get at here is there is this way of the electron being, there is this way, there is this way, but there's nothing in between those two. It's either this or this. It's either this or this, or this or this. There is no 1.4. There is no 1.88. There is no 2.76432. It's only 1, 2, or 3. The electron could be this, it could be this, it can be this. And I can change between those by doing something to the electron and going from a certain frequency of kind of motion, oscillation, whatever you want to call this, to going to a higher frequency that I can either like plug in 10,000 volts, or I can hit it with light or do different things. Thank you, best friend, for your help. But this is going to be our initial state of kind of describing what an electron does within an atom. And we're going to make this a little more complicated because it turns out that an electron in an atom is not one-dimensional or two-dimensional or whatever we want to consider this, but an electron within an atom is actually in 3 dimensions. And so we need to take this kind of concept of quantization and be able to apply it a little bit further. Okay, so we're starting with this picture here. We have the electron in the first energy level state, second energy level, and third energy level state. What we want to be able to do is we want to be able to explain what was happening with the light. So in this, one of the interesting things is when the electron changes from this to this, it gives off red light. So let's see if we can look a little bit at what that picture might look like. So here's a computer simulation. And in this, we have an electron in a particular state for a hydrogen atom. Okay? And what we're going to do is we're going to hit play on this. And when we hit play, we're going to send light in. And that light, just like me shaking the slinky with my best friend, is going to cause this electron to resonate. It's going to start to change how it exists. And eventually, it's going to end up as something different. Now keep in mind that these are a little complicated shapes, and so it might not be exactly what you envision. And now it's going to change back. So now the electron is changing back to the original state, and it's now producing light, and this would be the electron giving off a particular type of light. Now it's important to note that if I change my frequency a little bit, that now when that light hits that electron, nothing really happens. It doesn't interact with it in the same way than when I had that in tune. So we start to see a distortion of the electron, but then it really doesn't do anything, and that light just continues on. And that's what happens when we see light interact with something where it just kind of travels through. And so unless we're at the particular frequency of light that matches the gaps between these levels, nothing's going to happen. So this explains why we can see red light but there's no orange, but there's no yellow, but there's no green. But then all of a sudden there is a blue or teal, and then all of a sudden there's a violet and a violet. And so this explains that quantization idea, but we want to take this a little bit further and kind of go, well, what does this actually look like a little bit more in the atom? Because this is a simple one-dimensional thing, we want to take it and put it into 2 dimensions. Okay, so now we want to take this, I don't know if you consider this one-dimensional or 2-dimensional, but we want to take this picture and apply it in 3D. What does this actually look like for an electron and an atom? So in 3 dimensions, it turns out that instead of just having kind of a up or down system like this for the waves, that there are 2 things that we have to consider. One are what we call angular loops, and one are what we call radial loops. And I'm going to consider a loop to be a part where it really goes up and down a lot. So here there's 1 loop, here there's 2 loops, here there are 3 loops. Okay. If you want an official term, we call those antinodes, which means not a node. A node is where the wave doesn't really exist much or where there's no change. So in 3 dimensions, we're looking at 2 things. Now, when I say an angular loop, what I mean is that I mean the kind of, if you take your hand and kind of move it at different angles, all of a sudden at this angle there's a lot of motion, and then it goes back to none. And so this would have 1 angular loop, okay? And then in radial loops, what I mean is kind of as you move away in all dimensions. Now this is a 2D drawing, it really should be 3 dimensions, but I want to get the point across. So as I move out radially, that I end up with a spot where all of a sudden there's a lot of motion going on, there's a loop, and then all of a sudden I have a node, and then I have another loop where I have a lot of motion going on. So this would have 2 radial loops, this would have 1 angular loop, so to speak, okay? Cool, so let's actually look at what some pictures of that look like. So we have a rule that the number of angular loops is L, and the number of radial loops is J. And the 2 of those add up to be what the energy is. Okay, so which we can kind of think of as this 1, 2, and 3. So it turns out that when we have no radial looping going on, we call that an s orbital, is the name of it. And in the first energy level, because the L is 0, we have 1 of those things, so we call this a 1s orbital. And the 1s means that there's kind of 1 of these, so you wouldn't see this kind of gap here, you would just kind of see electron density as you move away, and then it would kind of slowly reduce. And then we would have another one, a 2s, that would look kind of like this. If we were to go up into our next level. And we would also have a 3s if we were to go up into the 3rd energy level. Okay. Now, for the 1s, we would have only 1 radial loop. The 2s would have 2 radial loops like this, and the 3s would have 3 radial loops. And so as we go from 1s to 2s to 3s, our electron density shifts to go further away from the nucleus, and therefore higher in energy. Now, for the second type of orbital, when L is 1, we call this a p orbital. Those are just letters, so don't get hung up on what they stand for or mean or anything like that. But a p orbital looks kind of like this, where we have an angular node and then kind of an angular loop. Okay, so in this case, what we're saying is that we already have L equals 1, which means that if we're going to have any kind of radial loop, we're going to have 1 plus 1. So this is not actually going to start until the 2nd energy level. So there is no 1p set of orbitals, there are only 2p orbitals. Okay, where the orbital is kind of this wave description of the electron. And then if we go a little further, we can have a second set of p orbitals, but it's going to be a little weird. It's going to be this kind of shape, it's going to be a little further out, and there's going to be kind of a radial spot where it kind of goes through a loop, then a node, and then another loop. So we can have a 3p set of orbitals. And we'll look at pictures of these, try and straighten them out as we go. Now, if we were to go 1 step higher, we end up in d orbitals, which are a little bit different shapes. So I'm not going to try and draw them. But you can see that if we get into d orbitals, because L is 2, there are not going to be any d orbitals in the first energy level, nor the second. So it's not going to be until we get to the 3rd energy level that all of a sudden we're going to start to see d orbitals. And they're going to look a lot more complicated because now we're going to have 2 sets of angular loops within them. All right, so let's look at some pictures and see if we can make sense of this a little bit. So let's switch over. We're going to look at some s orbitals. So these are the same pictures, just zoomed in differently. This is the 1s orbital where you're zoomed out as much as possible. What you can see here is that you have this radial loop. There's no angular loop to it. It's all just the same as we kind of go around. And then as we zoom in further and further on it, we can kind of see that there's this spot at the center where there's nothing, a node. And then we kind of move about, we get a larger and larger amount of electron density, and then it kind of slowly shifts back. Okay? So in this picture, the 1s would be kind of, here's your nucleus. As you move away, you get more and more electron density. And then it kind of slowly, as you get further away, decreases back towards 0. Now in the 2s state, here's our most zoomed in one. It starts kind of looking a little similar, but it's a little bit bigger. So a little further from the nucleus. The pictures are always in line with each other. But then as you zoom in, you start to see that there is a radial loop, and then a node, and then another radial loop. So this is a 1s orbital state. This is a 2s orbital state. We can see that here. We kind of have this node at the nucleus, and then as we move away, we have a radial loop, and then a node, and then another radial loop. So we have, this is the second energy level s-type orbital. Now when we go to the 3s down here, now we can start to see some of those even when we're zoomed in or zoomed out. But as we get a little bit further out, you can see here that you have a radial loop, node, radial loop, node, radial loop. So we have 3 different things, and therefore that is a 3s orbital state. Now that's the simplest kind, so let's go ahead and switch over and we'll look at some p orbitals and d orbitals. So when we talk about having an angular loop or an angular node, here's the angular node on the first, this is the 2p orbital. So we have this kind of dividing line where there's no electron density in this way. So sometimes this orbital would actually be given a qualifier, something like 2px. If we considered this the x direction, or we could do 2py, we could rotate it, or we could rotate it in and out of the plane and have a 2pz. These actually come in sets of 3. So here we have this line dividing it, and then we've got the 2p orbital. And as we kind of zoom out, you see that there's no radial loops except for the one. So we've got one radial loop, one angular loop, and therefore a total of 2 second energy level. That is a 2p orbital. And then we move down to here, and this is the 3p orbital. So here we have that same angular loop and node that this goes with, but now when we zoom in, we start to see that there's also a radial one. So we start at the nucleus, and as we move out, we get a radial loop, and then a radial node, and then a radial loop. So there's 2 radial loops as we move out radially, and there's 1 angular for a total of 3 things, and therefore it's the third energy level p orbital. This is the 4p, and here we have our angular node and our angular loop, and then we have a little views if we zoom in here. So here we have kind of a radial loop, and a radial loop. So it's 3 radial loops, 1 angular loop, so a total of 4, and that's our 4p. So these are descriptions, mathematical descriptions of what the electron is doing, and what we find is that when we take these descriptions and apply them, we can actually explain what was going on with the hydrogen back there, and we can actually go on and explain other elements too on what kind of light they produce. So when light comes in and interacts with these electrons, it can change between these, although there's some rules depending on which transitions you can make and which ones you can't. So sometimes it takes multiple steps to be able to go between any 2 orbitals you want. But we can actually match up to all of our experimental evidence of what colors of light we get by construing these pictures. Let's look at some d orbitals just for fun. All right, so here we have our d orbitals. So now you can see that there's kind of a radial node and an angular node and an angular node. So we have an angular loop. Okay, so we've got 2 of those. So L equals 2. And then here we just have, as you move away radially, you just got one thing. So we've got J equals 1. So this is a third energy level orbital description of the electron. And we would call this designated as 3D. And these actually come in sets of 5. So you'll have 5 orbitals like this that can all coexist in the same energy level. And they differ in space a little bit. We have another magnetic angular momentum number that we can attach to this. But here is a second d orbital set, but in this one you'll note that there is 2 radial loops as we move up. And so this would then be a 4d orbital, And we would have a new set of 5 orbitals when we get to that 4th energy level. Okay. So if we go back to our picture that we originally started with, what we're saying is that in a hydrogen, or any atom for that matter, that we have this combination of these two types of loops that we were describing earlier with the slinky that allow us to then go through and explain exactly what's going on with light and how the electrons are working within the atom. We're treating them very much as waves in this case, although the electron itself is really not a wave or a particle, it's just its own thing. Here we're describing them as waves, and it's working out really well for us. And so we're ending up with situations where we can match a lot of experimental evidence, and we can predict and we can explain things really nicely by doing that mathematical treatment. Really, the electron's just an electron, and we can't really see what it's doing on, as per our grapefruit conversation earlier. So in this case, we can go back now, and now we have these descriptions of what our electrons are and what they're doing that allows us to be able to go back and tie in to what's going on when we look at light interacting with matter. Now this picture even becomes more complicated than this, because you can have molecules instead of atoms, and we can look at more complexity to other things that are going on besides just the electronic levels for the electrons. But having this kind of prereq allows us to go into what an electron configuration is, why certain elements do what they do, why they stick to each other, why they bond with different things. So there's a ton of explaining power that originates from this treatment that we've gone through here. All right, so to kind of tie in everything together, well, I've drawn 2 little graphs here, and these aren't the best graphs, but basically we've got the 1s orbital description where we've simplified it down from a 3-dimensional picture or 2-dimensional picture, cross-section, to a single 1-dimensional picture. So this is kind of the wave function described for a 1s electron. So in this, we note that as we start at the nucleus, we have a node. As we move towards really far away from the center of the nucleus, we have a node. And in between, we have this radial loop. So as we change our radius out, we change kind of what's going on with the electron, like this. Okay. In a 2s, on the other hand, we have this kind of radial loop, and then a node, and then we have a second radial loop that's a lot bigger, which means that the electron is now shifting where it's more likely to be further from the nucleus than it was up here, and that's where we kind of tie into these pictures that look like this, where these 2 things are these 2 things. Right now, it's not as fruitful to go through with a p orbital. You can't really pull that out in the same way that you can here. But when we go from being in a 2s state to a 1s state, or 1s to 2s, light is the thing that causes those electrons to change, as long as the light is at the resonant frequency to cause those things to change. So the last thing I thought we could do here is I'm just going to put up a couple pictures, and if you want to try and come up with what you think those are, whether they're S, P, or D, whether they're 1, 2, 3, 4, or 5, and if you want to go through and figure out what the J values and the L values are, that might get you started, and then eventually come up with what those are, and then you should be kind of on the road to understanding what an electron is doing within an atom, to a point where you can now explain the different things you're going to see about atoms. Okay? So if you want to take this a step further, you can go ahead and I'll put a link to the electron configurations video that will take this to the next level and connect it back to simpler chemistry beyond this really difficult stuff.